Hello everyone, hope you guys are doing well. I'm Srihari Desai and in this video I'll be explaining about hazards in combinational logic circuits and about static zero hazards. So let's get started. So in this video we'll be learning about what combinational circuits are, what is meant by a hazard, what are static zero hazards, and how we can tackle them. A combinational logic circuit is one whose output solely depends on its current inputs. This means that unlike sequential circuits, combinational circuits depend only on the currently provided inputs and not on the previously derived outputs. It consists of logic gates whose outputs at any time are determined from only the present combination of inputs and they have no memory. And since they don't have any memory, they don't store the outputs of the previous cases. These circuits are developed using AND or NOT, NAND and NOR logic gates. A combination of these basic gates lead to the formation of different kinds of circuits. It is time independent, which means these circuits do not have a clock signal to control the outputs. The output changes immediately with the change of the input. And lastly, they do not have any kind of feedback mechanism to feed the output back to the input. Here we can see a basic arrangement of a combination logic circuit. We have n input variables and m outputs. The outputs are dependent on the types of gates used in the circuit and the fashion in which they are arranged. Here's an example to show the same. Here in this arrangement we have A, B, C, D, E and F as the inputs and S as the final output. We have a combination of OR and NOR gates here, which based on the required computations give us the outputs S. So now we have a basic understanding of what a combination logic circuit is. In theory, these circuits should give outputs that are instantaneous and unique to the type of inputs given. But in reality, we see some kind of undesired variations in the outputs during the change of inputs, which we term as hazards. So now we'll be looking into hazards a bit more in detail. A hazard is an undesirable effect caused by either a deficiency in the system or external influences in the circuits. Logic hazards are a form of problems in which changes in the input variables do not change the output correctly due to some form of delay caused by logic elements, NOT, AND, OR gates, etc. This results in the logic not performing its function properly. Now, we'll be learning about the different types of hazards that we could see in the combinational circuits. There are mainly three kinds of hazards that we usually come across. Those are termed as static, dynamic, and functional hazards. Static hazards. A static hazard is a change of a signal state or an output twice in a row when the signal is expected to stay constant. When one input signal changes, the output changes momentarily before stabilizing to the correct value. Dynamic hazards. A dynamic hazard are a series of changes of a signal state that happen several times in a row when the signal is expected to change state only once. And lastly, we have functional hazards. Functional hazards are the ones caused by a change applied to more than one input. Now, with respect to static and dynamic hazards, we have ways to eliminate them. But since in functional hazards, it includes the change of state of multiple inputs, there is no specific logical solution to eliminate them. So now, we'll be looking into static hazards a bit more in detail. A static hazard takes place when change in an input causes the output to change momentarily before stabilizing to its correct value. For example, if the signal level that is 1 initially, due to some static hazard changes from 1 to 0 for a small amount of time, this is termed as a static hazard. This can also be in a reverse fashion where a signal level that is initially 0 changes from 0 to 1 for that particular moment of time. So in static hazards we can see two types. A static zero hazard where the output that is initially 0 momentarily changes to 1 before settling down to 0 when the inputs change. And then we have static 1 hazard. The output that is 1 momentarily changes to 0 before settling on to 1 with the change in the input. Now let's understand the static 0 hazard with an example. Here we have a circuit that is arranged in the following fashion. The inputs A, B and C are initially taken to be 0. We also have this timing diagram that represents the propagation of the signals through the gates. The propagation delay through every gate is taken to be d. Let's start with the input C. Initially, as C is 0, the x and y values are found to be 0 and 1 respectively. When these outputs undergo the AND operation, we get f to be 0, which can be seen in the timing diagram. When C changes from 0 to 1, there is a delay d seen before the change in C' and x. This is due to the delay in the NOT gate and the OR gate. At this moment, we see x and y to have the same signal level, that is 1. This leads to f switching to 1 for that particular time frame. After the signal C' passes through the OR gate, we see the value of y changes to 0, thereby reverting f back to 0. This can be represented in the timing diagram as shown. If we see the Carnot map for our circuit, we can see the opportunity for a static 0 hazard. There are two adjacent but non-intersecting minterms for the 0 outputs, highlighted by the blue and tan shading. For a product of sums logic function, any two adjacent zeros that are not covered by a shared minterm can result in a static 0 hazard. The logical function from this Carnot map can be seen as shown. Overcoming static 0 hazards. Now this brings up a question. Why is it important to overcome these hazards? These errors last only for a small period of time and they don't cause any change in the overall output of the system. So why is it important to remove these? Let's say such circuits were a part of a bigger unit. If they cause such errors or hazards in the system, these might lead to a ripple of such errors being passed on to the system. This propagation of these ripples might lead to a magnification of these errors and may lead to an overall error in the final output. Hence, it's very important to make sure to eliminate these. We can eliminate the static 0 hazard in the circuit by adding an additional grouping around the two adjacent terms as illustrated by the red highlighted box. From a pure digital logic perspective, the third sum term in the series is unnecessary and might be called redundant. However, from the additional sum, a dash plus b dash remains 0 when both a and b are 0. Thus, it is not affected by the change in C that has previously caused the static 0 hazard. The expression that we get after making this change is as shown. Using this redundant logic, we can create a new circuit that performs the same logic function but without the static 0 hazard. This new circuit is as shown. Although such kind of arrangements might lead to an increase in the number of electronic components or gates, this ultimately leads to a reduction of hazards, which helps in providing a more accurate result. Hence, it's very beneficial. So this brings us to the end of this video. Hope you guys were able to learn. Remember, a good student is always learning. So keep healthy, keep smiling, and have an awesome day.